Alright, hello folks. This is my third lecture about kinetics, and we're going to talk about more about the differences between zeroth first and second order reactions and integrated and differential rate laws, and we're going to do a little bit of calculus-ness descriptions so that you have an idea of why they are called differential and integrated rate laws. So the main point of this is pointing out that the set of equations that we use for each order of reaction, the differential, the integrated, and the half-life equations, they're all mathematically derived from each other, and they're not just an arbitrary set of equations. So here is my sort of calculus summary of what you're going to learn in calculus class next year. So one thing that you need to know is there's kind of a series, a list of 4 things here, a list of 4 graphs that go in order. Graph number 1 is a cubed graph, followed by a squared graph, followed by a straight line angled graph, followed by a straight line flat graph. So x cubed, so a cubed graph, a squared graph, an x graph, and a flat graph. And it goes in that order, and that order represents taking the slope of this cubed graph at each point and graphing it. And what you find is that the slope increases more and more rapidly as you go up on this x cubed graph. And so the graph of that slope shows this shape, a squared shape. And then you can do that again. You can say, I'm going to graph the slope of the squared graph here, and when you do that, what you find is that the increase in the slope of this graph is a constant increase, and so you have this increasing slopey graph here, but it is a constant increase, so it's a flat increase instead of a increasing increase, if that makes sense. And then you look at that graph and you go, okay, what is this? And I'm going to graph the slope of this graph at every point. And the slope at every point in this graph is the same slope. And in fact, it's 6, which if you look at this, you can tell it would be 6 anyway. This is y equals mx plus b again, so m is 6. So that's what this series of graphs is, and it's the cubed, squared, x, what? To the 1th and to the 0th power. Yeah, the cubed, the squared, the 1th, and the 0th power. And the place that calculus comes into this is when you take the slope of a function, that is called differentiating that function. So taking the slope of this function, you differentiate it to get this function. And then you go again, you take the slope of this function, the 3x squared function, you differentiate that, and you get this graph, which is the slope of it. And then if you wanted to go again and take the slope of this graph and differentiate it, you get this graph. So that's how you move down, and that's differentiating, and that's related to the differential rate law. You can also go up and say, all right, so if I have a graph of a slope of some function and that graph is flat, then I know that it comes from a graph that looks like this. And so going from a flat line graph to an angled line graph, that's going up. That's called integration, and the way that you would do that is by finding the area under that curve at each point. So it's easy for these flat guys because for the graph y equals 6 at point 2, you go, okay, what is the area under this curve? That is this rectangle, and that's going to be a 2 by 6 rectangle, so that's 12. So you go out to 2 and you'd point 12. At point 4, the area under the curve at point 4 is a 4 by 6 rectangle, and so that's 24. So at point 4 you put 24. Boop. At point 6, it's a 6 by 6 rectangle, and so that's a 36 size point, and so you go 6, boop, 36. So you end up making this graph going up from the 0th power graph to the 1st power graph is called integration, and you do it by doing area under the curve. And you can do that again. You can go, okay, well, heck, let's do it for this triangle thing here. So this is a triangle of 2 and 12, and so that's 1/2 base times height. So 2 times 12 is 24, but then that half of that is 12. So this is going up a graph, you've got a 12. At 4, that's 4 times 24. So that's 4 times 24 times a half is 48. So that's 4 and 48. And so you can see that makes this curve. And so you're going up integration. And then you do it again, and it's sort of harder to do the integration by hand on a squared graph because the shape is a curvy shape instead of a nice triangle, and that's harder, so we're sad. But you can do it. There's a way to do it. And so you can integrate the x squared function and find the area under this curve, and you get the cubed function. So there's a way to go down by finding the slope, and there's a way to go up by finding the area under the curve. Going down, finding the slope is differentiation, and going up, finding the area under the curve is integration. And the way the order of the graphs goes is very curvy, slightly less curvy, straight line, flat line. Okay? You need to know that. Now that you have learned all of calculus, we can now talk about kinetics again. So, for zeroth order reactions, and a lot of this is reiteration and firming up of your concepts about the zeroth first and second order reactions. You have seen a lot of these little things briefly before. So for a zeroth order reaction, the integrated rate law, which if we think about the integrated rate law, we remember that it's concentration versus time, so you've got time in your equation. That's concentration of A at time t is equal to however much you started with, however fast it goes, which is the rate constant, and how long it's been. So that's what that is. And what you can observe about a zeroth order reaction is the amount at any point in time decreases linearly. You're going to lose the same amount every second. It just goes down, 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 and then it's done. It doesn't go down, down, and slow down as it goes. It goes. So the amount that you lose every second doesn't change. And the differential rate law that matches this integrated rate law, the zeroth order differential rate law, you can see that because the rate is equal to the rate constant. How is it related to the concentration of the reactants? It's not. It's to the zeroth power. This is k times a to the zeroth power. So the only thing that matters is nothing. It just goes. The concentration does not affect the rate. And typically what this implies about the mechanism of the reaction is that the slow step, the one that you're waiting around for, is catalyst based. And so, you're waiting on the catalyst to get something done. It doesn't matter if you increase the concentration of your reactant, that catalyst is the bottleneck. So you're kind of going, come on, I wish I had more catalyst, but you don't, so oh well. So here's a graph of concentration versus time. This is a graph of your integrated rate law kind of stuff, so your y equals mx plus b thing here, where your concentration is on the y-axis and your time is on the x-axis. And what you can see with this is, can I zoom in? I can zoom in. Where's my zoomy thing? Zoom. Zoom? Zoom. Ooh, too much zoom. Too much zoom. Less zoom. Okay, that was really slow. Okay, that's pretty good. All right, what you can see with this is that at time 0, you have 0.2 molar reactant A. And by the time you get down to like 66 seconds, all of it is gone. How much did you lose in 20 seconds? About let's see. How much did you lose in 22 seconds? About a third of it. How much did you lose by 44 seconds? 2/3 of it. It just goes boom. What's important to see about a zeroth order reaction is that the line is already straight. And so you can figure out your k by calculating its slope, because y equals mx plus b. There we go. Another thing that you can see is that starting at 0.2 molar, one thing that you're often interested in is the half-life, which is the time it takes to get to half the concentration. So the half the concentration in this case is 0.10. So the first half-life is at 0.10, and that time is about here, so 20, 30, looks like, I can't read this graph, 34 seconds, something like that, okay? The second half-life is going to be the time it takes for that to halve again, so from 0.10 to 0.05. And so that's going to be, to 0.05 is going to be from like 34 seconds to 50 seconds, which is about 17 seconds, which you may notice, 34 seconds, 17 seconds. That half-life is shorter than the first one. Then the third half-life is going to be at 0.025, which is right here on this, in between these two blue lines here. And that's from 50 seconds to about 57, 6 seconds, something like that. 58 seconds? Let's say 58 seconds. So it goes from 34 to 17 to 8. So what's neat about a zeroth order reaction is that you can, number one, look at it and go, oh, that's zeroth order because it's concentration versus time and it's straight. The half-lives keep getting shorter. The half-life is half as long as the previous half-life because you're losing the same amount every second, and you're losing and losing and losing and losing, and so it doesn't take quite as long to lose, it takes half as long to lose 0.05 as it took to lose 0.10 to begin with. And your half-life formula is, I need to be over here. I can't be over here. Maybe I can move this thing. Oh well, I don't need to zoom in anymore. Okay, there we go. My half-life for a zeroth order is the time of 1/2, so the half-life is equal to the concentration at time 0 divided by 2 times the rate constant. So that will be helpful if you are ever asked for that. Alright, okay, and now the reason that I have this graph is to sort of explain the graphy mathematical relationship between the integrated rate law and the differential rate law, which the differential rate law is the differentiated version of this graph, so the slope of this graph. And so what you can see is the slope of a straight line is a flat line, if you remember that from our little calculus lesson. And so this is the differential rate law here. The rate is equal to k, and that's this. The rate is equal to k. So differentiating this graph gives you this equation. So these are tied together by that calculusness that we discussed earlier. Alright, next we have some more about the first order rate. First order. What does this red dot mean? I don't know. Hey there, red dot. Alright, first order reactions. For the first order reaction, you've got some slow step that involves the reactant that you're concerned about, a unimolecular step to the first power, and the integrated rate law for that kind of reaction is ln of a is negative kt time plus ln of a at time 0. And so what they're saying is, you know, how much do you have at a certain time is related to how much you started with and the rate at which it goes and how long it's been, which is totally sensible, which is very nice. For a first order reaction, the amount at any point decreases exponentially speaking. So the concentration decreases and it slows down. And the slowing down that it's slowing down with is a consistent slowdown. So it's going boo, as opposed to the zeroth order, which was, which was boop, 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 boop. So we have more of a boo with the first order reaction here. And what you can look at with this graph is you started with 0.2 molar again, but for this reaction, when it's first order, it matters how much concentration you've got. So this reactant, you start off with 0.2, you have a certain rate, but then when you get down to 0.15, it can't go quite as fast because you're waiting around for it to hit itself. And so it's got to slow down, so the slope gets less, and then it slows down and you finally get to 0.10, but now there's even less, and so it's going slower, and then it goes slower and slower and slower and slower. So that's the idea for a first order, and you can see this is the x squared shape, which is not quite as curvy as the cubed shape. So this x squared shape is what you get when you try and graph a first order reaction, just the concentration versus time. If you want to make it a straight line graph, which you often do because you'll get a question that will give you data and they'll ask for k, you can't get k except off of a straight line graph. So you might want the straight line graph, and the way to do that is to graph the natural log of the concentration of A versus time. This is the concentration versus time, and you get the But the natural log of the concentration versus time gives you a nice linear graph. It's a negative slope. It's going down, right? So that's why you've got this negative k here. There's this negative k. And so forcing it to be straight by ln'ing it is often useful so that you can get the k out. So that's that. And then the other thing that you can do with this graph is look at the slope of it at every single second. And what you do is you differentiate it, and you end up with this graph. And when you differentiate the slope of x squared, you end up with a straight line, which is x. And so you end up with this line here. And what you can see is that the rate is related to A in a linear fashion. Nice line here, and here we've got that. Rate is equal to A in a linear fashion with a slope of k. Bam. So this is the differential rate law. This is the integrated rate law. They're tied together by calculus. Woo! The half-life is the ln of 2 over k. And what's really cool about first order reactions is that the half-lives are the same length every time. Because it's slowing down, you end up with, this distance here, this time distance, being the same size every time you cut it in half. So let's see if I can zoom in again. Let me move this up here. Can I zoom in? Come here. No. Can just open a big menu, huh? Alright, come here. So what you can see is that to get from 0.2 to 0.1, that took 7 seconds. The next half-life is going to be from 0.1 to 0.05. From 0.1 to 0.05 was from 7 to 14 seconds, so that one was also a 7-second half-life. From 0.05 to 0.025, that's from 14 seconds to 21 seconds. That's the third half-life, and that's also a 7-second half-life. That's going to continue. It's going to go cut in half every 7 seconds, cut in half every 7 seconds, cut in half every 7 seconds, until you get teensy-weensy concentrations, and then you wonder what happens to the last atom, don't you? This is the sort of behavior that is observed with radioactive decay. So if there's ever like radioactive uranium, what you see is that it's a first order reaction where it goes and slows down. But you end up with the half-life, the amount of time it takes for half of it to decay, always being the same. And so that's why they're able to use half-lives as kind of a clock, a radioactive clock, for the decay and dating of things. Alright, now let's get back to regular size. Alright, so that's first order, and then finally second order reactions. This is the inverse of the concentration of A equals KT, not negative, KT plus the inverse of A at time 0. This one, the concentration is decreasing more and more slowly as time goes on. With a first order reaction, the slowdown was a consistent slowdown. With the second order reaction, the slowdown is a more and more slowly as time goes on. And so that is a x cubed shape for the curve. You'll notice this is a curvier curve than this curve. This is the cubey curve. This is the squarey curve. And let's see, the converting it to force it to a linear graph is the inverse versus time, and that will give you a linear graph, and so you can pull k off of that graph if you need to. In order to get your half-life, that's your half-life is equal to 1 over the rate constant times a at time 0. And what's neat about this one is that with a zeroth order, if you remember, the half-lives get shorter. With a first order, the half-lives are the same length. With a second order, the half-lives get longer. It's kind of cool. Isn't that cool? Cluck. Yeah, that's the half-life. The half-lives get longer. And let me zoom in. You just zoomed out. Shh. All right. So what you can see is that from point 2 to point 1, your half-life is, let's see, this is a different scale, is like 25 seconds. And for your second half-life, you're going from 25 to, no, not 25. 20, 40, 60, 50 seconds. 50 seconds. And for your second half-life, you're going from 50 to 150, so that's a 100-second half-life. And from this one, it's 150 to 350, so this is a 200-second half-life. So you can see the half-lives are getting longer and longer. And in terms of the relationship between the integrated and the differential rate laws, if you graph the slope of this QB graph here, you will end up with the rate versus the concentration, and what you get is a squared graph. This isn't a very beautiful squared graph because I had to draw this in paint, so this isn't a perfectly shaped squared curve. But that is what you see when you go up here. The differential rate law tells us that the rate is related to the rate constant times a in a squared fashion, and that is what you are seeing in this graph. All right, now for some problems. And I'm going to switch over to my black pen screen. There we go. All right, using the graph at left, determine the instantaneous rate of disappearance of reactant A at time 6 seconds, which is at, well, it's not blue anymore, it's yellow, and also at time 17.5 seconds. Explain the difference and what it means. If you remember from math class, the way that you find the slope at a particular point on a curve is you draw the line tangent to that curve, and I'm going to do that, and it's not going to be pretty, but you should be doing this with a ruler. And where does this go? That goes to about here. So the slope here is what I found was that y is so the slope here is the rise over the run, and this is a very wiggly version of the triangle that you would actually draw with a ruler for your slope. And when I did mine on paper and it was real pretty, I found that the change in y was 0.07 and the change in x was 7. And in fact it's negative 0.07 because it goes down. It's a negative slope. And so you end up with negative 0.07 divided by 7, and you get a slope of negative 0.01. And the rate is equal to the negative of the slope. So the rate at 6 seconds is 0.01 moles per liter per second. And at 17.5 seconds, which is here, you've got a triangle that looks more like this. That's the tangent there, and I found with my triangle that I drew beautifully on my paper that that is about 0.025 in 7 seconds. And so I found that at time 17.5 seconds, my rate, which is the negative of the slope, is 0.0036 moles per liter per second. Now, what this difference is showing and what it means is that at an earlier time, your rate is bigger. So at 6 seconds, you're losing 0.01 molar per second. At 17.5 seconds, you're losing about a third of that. So it's getting slower and slower. And the reason for that is because when you have lost so much of your reactant that's important, it's not going to react as fast because you have to wait longer for the collisions that are required for the reaction to happen. You have to wait longer for them to happen. So that is why the rate goes down in this graph. All right, based on the graph, what order is this reaction? Just by looking at a graph of concentration versus time, first of all, we can tell this is not zeroth order because a concentration versus time graph of zeroth order is straight. This is first or second order, and so we can kind of look at it and go, well, does it look squaredy or cubey? Or what you can do is you can see what is happening to the half-life. And so for the half-life, you go from 0.2 to 0.1. That takes like, I don't know, 6 or 7 seconds. And then for the next one, from 0.1 to 0.05, so from 0.1, which is about 7 seconds, to 0.05, that's about 14 seconds. That one is also 7 seconds. So what you can see is that your half-life is the same each time. And so you go, oh, gee, which kind is like that? Hey, first order. So this is first order in reactant A. One little skill that might pop up is this graph is telling you the concentration, the disappearance of reactant A. Sometimes you'll be asked for, well, A is disappearing at this rate. What is happening to B? What is happening to C? And so given the reaction, A plus 2B yields 3C. What is the rate of disappearance of reactant B? And what is the rate of appearance of product C? And the way you do this is you go, well, for 0.01 moles per liter per second of A, you've got moles of A versus moles of B. That's 1 mole of A, 2 moles of B. So it's actually moving at 0.02 moles per liter per second of B are disappearing. So B is disappearing twice as fast, which you can see. B is disappearing twice as fast. Look at that. C is appearing 3 times as fast. And so you go 0.01 moles per liter of A, and moles of A is 1, and 3 moles of C. And so C is 0.03 moles per liter per second. C is appearing at 0.03 moles per liter per second. B is disappearing at 0.02 moles per liter per second. One thing that they're real picky about is that rates are always supposed to be positive. And so while A is decreasing and C is increasing, the slope is the negative. They fiddle with it to force it so that they are all positive. So that they'll have you say, instead of including a negative, they'll have you say that this is disappearing. So there's sort of an implied negative, but you don't actually write it. So there you are. There's that. All right. And question 2. 3 different reactions were observed over time, and the concentration of the relevant reactant was recorded periodically. What is the rate law and the value of K for each of the 3 reactions based on the data given? All right. So for this first reaction, the concentration of A, what you can see is that it goes from 0.4 molar to 0.2 molar in 1 hour, 0.2 molar to 0.1 molar in 1 hour, and 0.1 to 0.05 in 1 hour. So that's 1 hour, 1 hour, 1 hour, and it has divided in half 3 times. So that's a half-life, a half-life, a half-life. They're all the same length. And you think, now which one is like that? That's first order. So this is first order. Your rate law for first order reactions is rate equals K times A to the first power. And the value of K, so we would have to stick in, wait, can I find the value of K? I don't think I have a rate. Do I have a rate? I have time and concentration. Oh, I'll have to use this thing. That's right, I can use my integrated rate law. So that's ln of a 0, no, at equals negative kt plus ln of a 0. So that's, let's see, a at 0 is ln of 0.4, and this is ln of, let's do this one. So that's ln of 0.2 equals negative k times 1. So ln of 0.2 minus ln of 0.4. And then, right? Yes. ln of 0.2 minus, no, not times, monkey face. ln of 0.2 minus the ln of 0.4 is equal to negative k times 0.1, so k ends up equaling 0.69. Let's see, and that's the rate law. There's the rate law. There's first order, and there's k. Okay, bam. So that's 1. 2. Here we've got every hour you decrease by 2. 8, 6, 4, 2. That reminds me of zeroth order, and if it doesn't you can also look at the half-lives. The first half-life took 2 hours, and the second half-life took 1 hour. The half-lives are getting faster. That is zeroth order. The rate law equals k, and your integrated rate law is at equals negative k plus a 0, so that's 8 equals, let's pick this one again, equals negative k times 6 of, no, k times 1 of 6. So 6 minus 8 equals negative k, so negative 2 equals negative k, so k equals 2. So there is my k, there is my rate law, and there is my zeroth. Alright, so that's reaction 2. For reaction 3, guess what this one is going to be? So here we've got 1 molar going to 0.5 molar in an hour. And then you lose a little bit more, but really I care about this. Here's my next half-life. So that's a half-life that's getting longer and longer. So this is second order. My rate equals k times a to the second power, and that means I use this formula. 1 over at equals, nope, no negative. See, there's that time that it comes up. Equals kt plus 1 over a0. And let's use this one again. So 1 over, oh, this one is nice. 1 over 1 is, and then k, and my time is 1. This is going to be really easy. Is 1 over 0.5. So that's 2 equals 1 plus 1. Man, that's really true. So k equals 1. So that's your k, that's your rate law, and it's second order. Bam. Alright, question 3. Using the following information, determine the half-life of this reaction, assuming there is a single reactant. This is another case of you are given data points, concentration versus time, and you are asked to graph them. You could graph them by hand, or you could use our handy-dandy calculator thing, which, let me go get that. Alright, here's my online calculator doohickey, so let's go to stat plot, edit my lists, change my list so that its time is 0 and 10 and 20 seconds, and delete that one, and delete that one, and go do this list, and let's hope that it's zeroth order. Let's see if it's zeroth order. Is it 2.0 is concentration at time 0, 1.3, and 0.9633, enter, and delete that guy, and delete that guy. This is going to be a pretty small graph, so we'll have to be very careful to make sure that it is actually linear looking. So let's go to stat plot and make sure that the thing is on. No, it is not on. Alright, we want it to be on. We want it to be mountain, and we want it to be list 1, list 2. Yep. Window, and my x minimum is 0, and I'm going up to 25 or so. can do my x scale of 5s, and my y minimum is 0. My y maximum is 3, and let's do scales of halves. And let's see if this sucker looks flat. It doesn't. That is curvy. Therefore, I have proven it is not zeroth order. Now let's go back and see what we think about first order. Alright, so if it were first order, it will be straight when I do the ln. So ln of 2, ln of 1.3, and ln of 0.9633. And now I need to go change my window for the y-axis to be between -1 and 1, so that all my y's show up. -1 and 1. Now let's see if this one is straight. Is that straight? It's not straight. It sort of looks straight. It's not straight. It's kind of curvy. There's this kind of a bend there. So let's go back and let's try it for second order and see if it's second order. It better be second order. Yeah, I know. I hope so. Alright, so this is going to be the inverse of 2. So 2 to the negative first, and 1.3 to the negative first, and 0.9633 to the negative first. Alright, and that goes from like 0 to 2 in my window. 0, 2, graph. Graph? It's not showing. What did I do? What did I do? It's from 0 to 2. What did I do to my window? Yep, that's not it. That's 0. Hee hee hee. That's 2. My y scale is 1. Now, there we go. How about that? Hey, look at that. How straight is that? It's so straight. Yes, I know. Good job, chicken. So that has just proven that this is in fact a second order problem, which means that we can go ahead and use the second order Halflife equation, which, if we remember what that was, it was 1 over k times a0. So, well, but I don't have k yet. Oh no, I have to go find k. Okay, fine. Alright, so I do have this as well. So let's do this. kt plus 1 over a0. So that's k times, let's do this one here. So 1 over 1.3 equals k times 10 plus 1 over 2. And you solve for that and you get k equals 0.0269. And then the question is, what is the unit for k for a second order reaction? And that's going to be moles, liters, and seconds, always to the -1. But what are the moles and liter exponents? And you go, well, when it's second order, you've canceled, you've got this deal, a squared, right, equals k squared. The mole per liter here will cancel one of these moles per liter, and then the other one will be upside down. So that's one of them. So it's one upside down mole and one on top liter. So that is your unit for k. That is great. That's k. So now we can stick that in here. So we've got 1 over 0.0269 times, what's my a0? 2. So the time for 1/2 is 18.6 seconds, which if you go back and look, that's about right. It looks like to get from 2 to 1, it's going to be slightly less than 20, and that's what we got, so we're happy. And what is the concentration after 5 minutes? You have to notice this is in seconds, so that's actually 300 seconds. So you go and just stick that sucker in. 1 over AT is 0.0269, that's your K, times 300 plus 1 over 2, and you solve for that, and you get A at time t is equal to 0.117 molar. Bing! That's it. Thanks, folks.